Hey guys, I wanted to put together a video in which I put together a little bit about photoelectron spectroscopy for you because in the lecture that guy went through it kind of fast. So hopefully with this additional information, it'll help make some more sense, okay? So basically the photoelectric effect was used because it was back in the early 1900s. Basically, Einstein explained it using Planck's quantum idea, right? That only a light at or above a threshold frequency will cause electrons. And they found that if they shone light on a metal surface, they could do it all day and nothing would happen. But once that light got to be a certain threshold frequency, electrons could be ejected from a metal surface. And so this kind of just shows you, here's our Roy G. Biv, and we're going to shine light. And then, so it's only when light is shown from at a certain frequency or a threshold frequency will electrons, eventually we'll get through this, okay, will electrons be emitted. Okay, and so the frequency of light is going to determine if the electrons are emitted or not, and with what kinetic energy. And then the intensity or the brightness of the light determines how many electrons are ejected. So we talked about the first ionization energy, and that is the energy that's going to be required to remove an electron from the outermost energy level of an atom. And why would it require less energy? So hopefully by this point you remembered our Coulomb's law kind of thing, okay? And it's going to require less energy to remove the outermost electrons because this distance is greater, and those electrons are drawn to the nucleus with less force because they're further away, right? And so if you kind of take a look at lithium, and you'll remember lithium has an electron configuration of 1s2, 2s1. And if you look at successive ionization energy, it's going to require much less energy to remove this electron than it will either of these electrons here. So core electrons are going to require a lot more energy to remove. And so basically what happens is as we remove electrons, it's going to get harder and harder to remove the next electrons. And so if a photon with sufficient energy hit the third electron for lithium, would it require that much energy to remove? Interesting. So photoelectron spectroscopy says that if an atom is hit with enough energy, any of its electrons can be ejected. Now, if you go back to that lithium example, as long as we exceeded that energy threshold of that third electron to remove, any of those electrons could be ejected. And so photoelectron spectroscopy identifies how much energy it's going to require to remove all of the electrons in an atom. And so the way that it works, basically X-rays, an atom is bombarded with X-rays, so the X-rays are going to strike a sample of the atom, and when a photon strikes an electron, the electron's going to leave the atom. So electrons that have a low binding energy are going to exit with a high kinetic energy, and electrons with a high binding energy exit with a low kinetic energy. Should make sense. So if the low binding energy, it's just going to kind of zip them out there and they're going to move faster, basically, is the way I think about it. And so the photoelectron spectrometer is going to compare the energy of the source, so this X-ray energy, and it's going to look at the kinetic energy of the ejected electrons. And the difference in that energy is going to be what's known as the binding energy of the electron. So when it talks about the energy of the photon, that's going to be the energy of the source, and then the kinetic energy of the ejected electron. So it's the binding energy for the electron. So in a photoelectron spectra, the binding energy is plotted against its relative intensity. And the key part about that is that the higher a peak, the more electrons there are that have that binding energy. And we can actually look at a photoelectron spectroscopy diagram and figure out how many electrons are at a certain energy level. And so this is kind of the way that this little kinetic energy analyzer would work, right? So these X-rays, all electrons are removed, and we will get a diagram that looks like this. This is the photoelectron spectra of lithium. Okay, lithium, notice there's a peak here for lithium, and there's also a peak over here for lithium. And the interesting thing about a photoelectron spectra diagram is that, notice the binding energy, it actually is lower on the right-hand side and higher on the left-hand side. I thought that the review video presenter did a good job of saying, hey, think about this as, like how close, if the left-hand side is the nucleus, it's going to take more energy to remove electrons that are closer to the nucleus. And so lithium, if you remember that the electron configuration, lithium has 3 electrons. So we have 1s2, 2s1. And so what we'll see here is, notice the lines here. We have 1, 2, 3, 4. At the peak height here is 4, and the peak height here is 2. So there are half as many electrons in our peak of lower energy than there are our peak of higher energy. And so we can kind of surmise then that this peak represents our 2s electron, and this peak represents the 1s2 electrons. So since there are twice as many electrons in the higher peak. And so we can look at an electron, a photoelectrospectrograph, and not be told what the element is, and kind of be able to figure it out by looking at the relative height of the peaks compared to each other, and looking at where they are on the energy kind of profile. So there's 2 peaks, right? A peak that is twice as tall is going to represent twice as many electrons. So here we are, okay? Here's our next one. We have boron, okay? Boron has 5 electrons. So the electron configuration of boron is 1s2, 2s2, 2p1. And so I think if you take a look then at this binding energy, okay, our lowest binding energy, or our would be closer to the right. So this is our 2p1 electron. This is our 2s2 electron. And this is our 1s2 electron peak. So hopefully you can see that. There are 3 peaks, and then how many electrons are represented by each. Notice that this is 1 electron, whereas there are 2 electrons in this peak, and there are 2 electrons in this peak here, and they are the peak corresponding to the 1s2 electrons and the peak corresponding to the 2s2 electrons are going to be twice as high as the peak for the 2p1 electron, because there are twice as many electrons. Okay. Which electrons are closest to the nucleus, right? Our 1s2, these electrons right here are going to be closest to the nucleus, and the 2p1 electrons, they're going to be the first ones removed when it's ionized. So our highest energy closest to the nucleus is going to be on the left-hand side of our PES diagram, and our lowest energy, or farthest from the nucleus, is going to be over on the right-hand part of our diagram. If we look at the PES of hydrogen versus helium, okay? Hydrogen, again, is a 1s1. Helium is a 1s2 electron configuration. So which peak is which based on what you know? And hopefully from that you can realize that this would be our hydrogen peak and this would be our helium peak because it's twice the height of the hydrogen peak. And why would the helium electrons be closer to the nucleus, let's say, than the hydrogen? And hopefully you have said, oh, wait, Mrs. Miller, that's because helium has one more proton than hydrogen has. And so those electrons, because of Coulomb's law, will be have more force and be drawn closer to the nucleus. So which is the helium? Yeah, okay. This is beryllium, okay. Beryllium, I'm looking on the periodic table here. My electron configuration of beryllium is 1s2, 2s2. And so notice that these peaks are the same height. Can you tell me which peak corresponds to the 1s2 and which peak corresponds to the 2s2? So I would put my 2s2 electrons here, and I would put my 1s2 electrons here, and I'm hoping that you would do the same. Okay, this is our photoelectric spectrum of carbon. Carbon is a 1s2, a 2s2, a 2p2. Notice all of our peaks are the same height, and so they all represent 2 electrons. And by this point, I hope you can tell me that these would be my 2p2 electrons, my 2s2 electrons, and my 1s2 electrons. 3 peaks of equal height, right? Okay. Nitrogen, we have a 1s2, a 2s2, a 2p3. So notice my peak right here is higher than the other two, which are the same height. So these are my 2p electrons. So these are my 2p3s. This is my 2s2. This is my 1s2. 3 peaks. Okay, oxygen would be a 1s2, a 2s2, a 2p4. I think we should have by the time we get to oxygen, and hopefully you can see that then. This is my 1s2, this is my 2s2, this is my 2p4. And then neon would be 1s2, 2s2, 2p6. So notice the difference in the relative heights of our peaks. So here's my 1s2, my 2s2, and my 2p6. 3. And then sodium. Sodium electron configuration wise is 1s2, 2s2, 2p6, and then 3s1. So can you look at the PES of sodium and determine which peak is which? So notice this is my shortest peak, so this is my 1 electron. But from an energy perspective, you should be able to see this is my outermost electron, so this is my 3s1, my 2p6, my 2s2, and my 1s2. And then, so predict magnesium, okay? Magnesium, the electron configuration of magnesium is 1s2, 2s2, 2p6, 3s2. So how many peaks would you expect? Hopefully you'll expect 4. The 1s2 will be closest to the nucleus. The 3s2 will be furthest away from the nucleus, with the 2s and the 2p in between. And so how many peaks do you expect? Hopefully you recognize that you would see 4 peaks, and then there would be 2 electrons, 6 electrons, 2 electrons, 2 electrons. And so you should see, if I can, if I were to draw it, I would make a peak here for my 1s electrons. I would probably put my 2s electrons here. Let's see, 1, 2, and then 1, 2, 3, 4, 5. So I put this one here, and then I might put my 3s electrons here. So my diagram might look something like that. Okay, argon. My electron configuration of argon: 1s2, 2s2, 2p6, 3s2, 3p6. And so we should see 1, 2, 3, 4, 5 peaks, and we see 1, 2, 3, 4, 5 peaks. So lowest energy, these are my 3p6s. This is my 3s2s. This is my 2p6s. This is my 2s2s, and this is my 1s2s. Okay.